Okay, so for my discussion for post, I decided to take the data and to do an analysis on the time it took to take the first exam and the scores of the first exam themselves. So I highlighted all that data. And the first thing I did was I just did some simple descriptive statistics. So for time, we have the number of 92 participants. The mean was about 81 minutes to complete the exam, and the standard deviation was about 22. And then for the exam scores, we had the mean was about 68% with a standard deviation of 14.5 if you round to 15, and then also the same number of 92. So just for a little backstory. So the first thing I did was make a histogram of each of these variables by themselves. So for time, I just separated them into categories of 10. So we start at 30, we go all the way up to 120 and 129 to 39. So I made a frequency table. I made these equal with bins, and then I sorted them to get the total of 92. And I just graphed that in a nice histogram. So as you can see, our round average time was within this 80 to 89 minute area. That was our peak. So that was the most common. And then for our exam scores, I did the exact same thing. I made a frequency table, again with equal length bins. Since nobody got above a 98%, I only made the last bin go from 90 to 99. And I did the same thing. I sorted them in a frequency table, and then I just made a nice histogram here. So as we can see here, within the 60 to 69 category, the average being about a 68% of the exam, we can see this peak in frequency here with about 27 people. So my theory, or the question I was trying to answer with this discussion post was, is there a relationship between the time it took someone to take the exam and the score they did? So I decided that my explanatory variable on the x-axis was going to be time, and that my predicted variable on my y-axis was going to be the exam score, because I wanted to know if you took more or less time, what would your predicted exam score be? So on this sheet, there's a lot going on. So the first thing I did was I brought back our nice descriptive statistics that I had on the first page, just so I could make sure, double check my math. For my correlation coefficient, I did the correlation function, and then I took all my x variables in time, and then all my y variables in exam scores, and I got a correlation of about 0.3. So that's a moderately weak to okay positive correlation. As we can see, it's not super strong. It's not going to be close to linear. It's nowhere near close to 1, but it's better than some. So I'm going to say it's moderate in its correlation coefficient. So then from there, the next thing I did was I put it all on a nice scatter plot. So here's my scatter plot. All I did was highlight all my data, and I went to insert and made the recommended chart, which isn't showing up right now, but I didn't make a recommended chart. I clicked here on the scatter chart, excuse me. And then I edited my values down, so the max value on score was 100 and the max value on time was 120. Then from here, after I had all of this come out, I just clicked on this and I wanted to insert a trend line. So I did add chart element, trend line, more trend line options, came down here, clicked display equation on chart. And so what happened is this nice red and blue trend line has appeared. So it can, as you can see, it's not a super clear linear equation, but there's definitely something, and it definitely trends positively. And then it gives us our equation. So basically what this equation says, our linear regression, is telling us that our predicted y value should be equal to 0.2141 times the x value plus 50.992. So then from there, I did a little bit of my own research and I put the x values with the predicted y values and then the actual y values so I could just see how all of the residuals were trending. That was just for my own research though, because I was interested. But, so, now thinking back to student number, ID number 5, so this person took 59 minutes to take the exam and scored about a 49%. So, that little star, that little bubble represents our student ID number 5. And so from there, I calculated their residual. So, well, first I calculated their predicted y value, what their predicted y value should be. So I took the x of time, 59 minutes, and I multiplied it in and I added. And so the predicted y value of the score this person should have got on the exam was a 63.64. Probably a 64 because it's 63.6. So then from there, I subtracted the actual value from the predicted value, and we got a residual of about negative 14.6. So that means that this person was 14.6 points below what our regression equation gave. And then finally after that, to get our residual standard deviation, all I simply did was I did the STEYX function to do, and I did our actual y values, so you started with the exam scores, and our actual x values starting with the time to get a residual standard deviation of above 13.758. So we could round that up to 14. So our residual standard deviation with the residual that we got up here actually trend perfectly if we round this to 14, and this is 14 to 15. So that's showing us that we're typically having 14 points above or 14 points below what our regression equation is predicting for us for these scores. And finally, for our squared value, I took the correlation coefficient of, I just rounded it to 0.3 in this instance, and I squared 0.3 to get 0.09. So that's saying we have about a 9% of the variability in this equation is accounted for by the regression. So if only 9% is accounted for, that means that 91% is unaccounted for, and that number would typically make sense with having this much variance between our predicted and actual values. So, thanks for listening.